my plan, we're going to finish up 2-6. We'll take some 2-6 questions because I know that we're halfway through and some of us probably started the homework by now. If not, no biggie. And then we'll talk a little bit about the test. And it's our day. Kiddo? All right. What's up, Knowles?
I have questions on 2931.
Right. We'll hit homework questions after I finish the rest of 2-6.
Oh.
Just because
yeah,
that's okay. No biggie. No biggie. Chanel.
Will there be a 2-6 homework quiz next class?
Yeah.
Okay. And then Wednesdays, right?
That's my plan.
Okay.
All right. So let's take a look at this. Again, we've been, the last, 2-6, we've been talking about these limits at infinity. So like, how do I evaluate a limit? When the x goes to either positive or negative infinity, what do I do with that? So here, we don't have that, right? X is going to 0 from the left. But if I try to direct substitute this, what's the problem?
Yeah. Undefined in the exponent.
Yeah, I get a 1 over 0, right? Which is kind of like infinity, right? So what do I do with this? This feels like something weird going on. So, well, I know that, both e to the x and 1 over x are continuous near 1. So I can do this and kind of push the limit inside the function. So like if I know what to do with this, I should be okay. So let's try to figure out what's going on with that part. Again, I can't do direct substitution on this, right? Because it's a 1 over 0. What would I do? Chanel?
This is probably wrong, but multiply by 1 over x. Well, no. This is 1 over x. So isn't that like the other day, like...
If it goes to infinity.
Oh,
right? If the x is
okay.
going to infinity, we can make that 0. But here we're going to 0.
What is up for like
Graph or table, right? I'm going to do a table because I'm going to pretend that like we don't have our graphing calculator for this. So we're getting close to 0 from the left. So maybe I start at like negative 0.1 and we'll get a little bit closer and a little bit closer. What is 1 over negative 0.1? Negative 10. Yeah, 0.1 is just 1/10, so the reciprocal is 10, and it's negative, so it's negative 10. What's the next one going to be?
negative 100.
Good. And the last one?
Negative 1,000.
Okay, so it looks like this is going to
Negative.
negative infinity. Everybody agree with that? So what I'm going to do is I'm kind of make like this into like a dummy variable. So I'm going to pretend this is going to y, or is the variable y, and we're going to negative infinity. Because what we just saw was this, right? So if I replace the exponent with just a y, and then go to negative infinity, it's equivalent to what I had before, right? Because I know that limit as x goes to 0 from the left of 1 over x is going to negative infinity. Is that okay with everybody?
So since the exponent equals negative infinity.
Oops, that should be a y there. Yes. So I'm just going to kind of like make a dummy variable I know the answer to the exponents. We'll just have, okay, well, then we'll make a new variable y, and the y will go to the answer to what's in the exponent.
Okay.
Chanel?
Wait, I don't understand what you did. Isn't it essentially the same thing? The y and then the y approaches negative infinity. Like, wait, like I don't understand why you did that. Like the variable thing.
Well, this I can't just, okay, so that equals negative infinity up there, right?
Yeah.
But I can't do this, right? That's not something you can do. You can't just plug negative infinity into a function, right? Like you're not allowed to do that. But what I can do is I can create a dummy variable, the y, and just have y go to negative infinity. And that's kind of my workaround, right? So this is like that, right? But I can't write that because I can't just plug negative infinities into things. That's not something we've ever done or you're ever allowed to do. Instead, what we'll do, well, we'll just create a limit out of this. So we'll just have y going to negative infinity for e to the y, right? And that's the same thing. And that's something we can write, right? So this limit seems to be going to e to negative infinity. This limit also looks like it's going to e to the negative infinity, right? So they're equivalent. What does writing it as the limit as y approaches negative infinity of e to the y allow me to do? It now looks like this theorem. So I can just say this is equal to 0. Katie? Yes, must be negative infinity for that theorem. The positive infinity version of this, Katie, you'd have to say the limit as x approaches positive infinity of 1 over e to the x. And that would equal 0. Mm-hmm. So you could do that with a positive infinity. Those two are saying the same thing. Am I good to move on to the next one? Yeah. Okay. I didn't want to rush anybody through if they were copying or still thinking. Let's look at this one. Here we have the limit as x approaches infinity of sine x. Ooh, Mr. Kulik, what do I do with this thing? What do we think? Can I do a direct substitution on this? No, because what do I do with sine of infinity? Oh.
You just have to make a table.
Okay, let's try making a table. What values of x do you want to pick?
Probably 5.
Okay.
0. Pi over 2. 5.
Okay. We've already got, do you want to do another one that's small? We're going to positive infinity here, folks. Right? This is 0, 1, 0. Does that help?
Not really.
Not really.
2 pi is the same as 0.
And 2 pi would also be 0 again, yeah.
Pi over 2.
Negative 1.
That's 5.
Okay, well, what's the graph look like? Great. So that's also a valid thing to do.
Oh, yeah, that's fine. More helpful.
So we know what the graph of sine looks like, right?
Oh, yeah, it's just. Does it approach anything?
Great question. Ah! So is it approaching anything?
Not really, no.
No, right? because it's always going to just be oscillating between -1 and +1. No matter how far you go, you can go a little further and it starts heading the other direction, right? Oh, it looks like it's heading to -1, but if you keep going further, it's going to start heading to +1. But if you keep going further, it's back to -1. And it's just going to keep going like that forever, correct?
Yeah.
So what should we say the limit is? Does not exist. Yeah. Now keep in mind, if this function were somehow dampened, like if I stuck a 1/x out front or something, now when we do this, like that sine wave is going to get, or that amplitude on your sine wave is going to get smaller the whole time through, so it's now looking like we're heading towards zero at that point. Is everybody okay there? So again, oscillating is okay. Oh, that's okay. Oops. What is all this gobbledygook down here? Oh, that's something I wrote for last time. Let's just get rid of that. See you later. Okay. So here we're asked the limit as x approaches infinity of x cubed, and the limit as x approaches infinity, negative infinity of x cubed. Again, I can't do a direct substitution here, right? My limit theorems for x going to positive infinities don't work for this, right?
Yeah.
So what do you want to do?
Make a
Sure. Or what else even?
graph.
Or a graph, right? If you remembered what x to the 1 or x to the third looks like. Kind of looks like this. So x approaching positive infinity, what is the y doing? Great. If I look at as x goes to negative infinity, what's the y going to?
Negative infinity.
Done. Is that okay? All right. Very good. So what's our takeaway here? That like in a direct substitution sense, like negative infinity cubed is just negative infinity, or infinity cubed is just like positive infinity, right? That's kind of the intuition that you're seeing, right? That's the kind of the takeaway. Let's look at this next one. We have the limit as x approaches infinity of x squared minus x. If we do that same kind of direct substitution thing, what do we kind of get? Well, I get infinity minus infinity, right? And you want to say that's 0. It's not 0. That's an indeterminate form, which is like how, and it's like this is how infinities work, man. It's part of the reason why this becomes difficult is because infinity doesn't work the way you want. Your intuition wants it to work in like a one-to-one world. I can't set up like a one-to-one correspondence between infinity and just be like, oh, take this one out and this one, and there's nothing left. It doesn't really work that way. You know why? Here's the real mind buster. There's different sizes of infinity.
Oh yeah, I used to talk about that. So.
Yeah, some infinities are bigger than others. Not relevant to this course, but there's orders of magnitude for infinity.
What do you learn about that?
Real analysis, probably.
Oh, okay.
Wouldn't that be like if two trains are going on for infinity, but one's going a lot faster or something? Would that be two different things?
Well, so if you think about, so let's think about this real quick. Okay, you have the set of integers and the set of even numbers. Which one has more?
7 and 8.
They're the same.
Yeah.
Because you can set up a one-to-one correspondence by just taking like the evens, we're just gonna, or the integers, we're just gonna multiply everything by 2, and that gives you the evens, right? And you can do the same thing for like the rational numbers. You can set up the same one-to-one correspondence. It's a much more difficult construction to do, but you can do it. Is he on my list? Is my Hall of Fame back here? Is Cantor on that list? Cantor's the one with the credited with the proof of this. I don't think he's on my list. But that's something he proved, as credited with. What you can't do is do a one-to-one correspondence between the real numbers and the integers. So it turns out there are more real numbers than integers. The size of that infinity is bigger than the size of the integer's infinity because you can't pair them up one-to-one. Now, this is beyond the scope of what you need to know. This is like a real analysis topic, but it's like one of those things that I think helps with your intuition of why infinity minus infinity isn't just 0. Because some infinities are bigger than others. Ugh. The name for the smallest infinity is called Aleph Null. It's named after the Hebrew letter A. If you're curious. Yeah. Well, there's not. It's just like Aleph 1, Aleph 2, where each one is like an order of magnitude bigger than the other.
Okay.
So like the complex numbers are an order of magnitude bigger than the real numbers. So it's like Aleph Null is like the integers, Aleph 1 is like the reals, Aleph 2 is like the complex numbers. And you just kind of can build out from there. Like if you did the cross product of complex numbers, where like you have an ordered pair where each component is a complex number that's like, another order of magnitude bigger, and keep on building. Anyways, let's look at this one. The whole point here was just saying that like infinity minus infinity isn't just 0. It's one of our indeterminate forms. See, it's right here. So what indeterminate means is that you can't, not that you can't really say, but the answer could be anything. So it doesn't mean it doesn't exist. It just means that if I have infinity minus infinity, I can set up a bunch of problems that work out to be infinity minus infinity, but actually have a whole different set of answers. Actual numeric answers that are not, or that are not necessarily the same. So it has to be a different way for me to do this.
Table or graph it?
Well, I can do this actually algebraically, believe it or not.
Oh, you just multiply by x squared plus x.
Well, I wouldn't do that. I would just factor an x out. Because what can I do if I have the product inside of a limit? This is one of our limit laws.
You get limit of x or limit of x minus 1.
Yeah, I can take the limit of each factor in my product. That's exactly right. Oops. Got the infinity there. So if I do the limit as x approaches infinity of x, what's that have to be? Just infinity, right? If you think about the graph of y equals x, it's just pointing up and to the right. What if we do the limit as x approaches infinity of x minus 1? What's that got to be?
Is it also
it's also infinity. If I think about the graph of y equals x minus 1, just a graph pointing up to the right. So if I take a gigantic positive number, like infinity, and I multiply it by another gigantic positive number, like infinity, I should get infinity. Which would match up with what you see if you tried to graph this thing, right? It's going to look like that. Or if we look at as x goes to positive infinity, go into infinity. Everybody okay there? Okay. Next example. You could, but I don't think that's going to be helpful in this case.
Just multiply top and bottom by 1 over x squared.
Okay. I wouldn't do 1 over x squared, though, because if I do that, the denominator is going to end up going to 0.
Oh, yeah. Just 1 over x.
Let's do just 1 over x. Yeah. Now that's an important thing that we just said there. So let's kind of repeat it, make sure everybody kind of caught that whole discussion, because it happened kind of quick. So originally Nolan suggested to multiply the top and bottom by 1 over x squared. And I said that I wouldn't want to do that because this would turn into 3 over x squared. That goes to 0. This would turn into 1 over x. That goes to 0. And I'd end up with a 0 denominator. I want to pick the biggest power of x so that my denominator is not 0. Nolan?
Wouldn't x just go to x over x, which is 1?
Yep, which is fine. No, I said if it was x squared.
Oh,
if it was x squared. Yeah. We're talking about why x squared was going to be a problem. Everybody's okay? So I can push my limits through. And if I evaluate these things, I'm going to leave this one here because I don't want to write infinity there. But the limit of a constant is just a constant, regardless of what x is approaching. The limit as x approaches infinity of 1 over x to the r is 0. That's one of our theorems. And the limit of a constant is just a constant. Yes?
Wait, the limit of a constant is just a limit law, right?
Mm-hmm. Correct, yes. So when I look at this, I basically have infinity plus 1 divided by negative 1, which it should just be a gigantic number plus 1 is still a gigantic number, but divided by negative 1 is a negative, a gigantic number, so negative infinity. Is everybody okay with that? Okay. Can I point out to you that if we were clever, we could have looked at this particular problem and not have to write anything down and come up with the answer in about 10 seconds. Let's show you how. Because if you're on a multiple choice question on like your AP test, that's a useful skill to have, right? If I can take 10 seconds on this problem, it leaves me, like an extra 2 minutes I can spend on something that's actually, I need to write stuff down for. If I look at this, what kind of function is this? From algebra, what? Well, it's a polynomial over a polynomial, right? We call that a rational. Remember from Algebra 2 or even pre-calculus, to find the asymptotes for a rational function, you compare the degree of the numerator with the degree of the denominator, right? There's 3 cases. If the degree of the numerator was greater than the degree of the denominator, like in this case, we're going to have the slant asymptote, right? So either it's going to go positive infinity if the line's sloping up, or negative infinity if the line's sloping down. To tell, what I would do is I'd think, okay, if I put a big positive in for the x's, the numerator is positive. But if I put a big positive in for the x down here, the denominator is negative. So it would say negative infinity. If the degree of the numerator is the same as the degree of the denominator, then I have a horizontal asymptote at leading coefficient over leading coefficient. So my limit as x approaches infinity or negative infinity would just be leading coefficient over leading coefficient. And if the degree of the numerator is less than the degree of the denominator, then I have a horizontal asymptote at y equals 0, which means that that limit would just be equal to 0. Which is a lovely shortcut to have for a multiple choice question, right? If I'm able to just look at this and go, okay, it's negative infinity or positive infinity, just let me pretend to plug in the big number somewhere and see if it's, if the refraction is positive or negative, and then I know which one it is. That's 10 seconds. I like that. Now, can you do that on a free response question? No, the expectation would be that you'd use calculus there. But on a multiple choice piece, where nobody's expecting to see any work, do it the most efficient way possible. Chanel?
I thought if the numerator is greater than the denominator, wouldn't you use I might be wrong, synthetic
that would give you the equation of that slant asymptote, that diagonal line.
Okay.
But the point is, it's the ends of your are going to be
we
following the diagonal line, which
really
means it's either positive infinity, or if it's going this way, negative infinity. You just have to determine which one it is. But yes, if you wanted to find that particular asymptote, yes, that's how you would do that.
Can you just go over one more time how you did the since the numerator greater than the denominator for this problem?
Yeah. So I notice that the degree of the numerator is bigger than the degree of the denominator, right? Degree 2 over degree 1. So I know that it's either going to be positive infinity or negative infinity in that case. So to figure out which one is which, I'm going to look at what this fraction is when I plug in a big number for x. So if I have big number squared plus big number, still going to be a positive number, right? If I do 3 minus a big positive number, that's going to be a negative number. So this fraction is going to be negative. That's why I know it's negative infinity as opposed to positive infinity. Is that cool? And now, if you've never seen anyone do that or use that as a way of thinking about whether something's going to be negative or positive, that's an unlikely way of coming up, thinking about this, right? To come up with that on your own. Having seen it now, it's like, oh, if all I really care about is the negative and positive, just kind of plug in a test value and think about it for a minute, and it should be enough, right? I don't actually care what the fraction is because I'm not actually plugging anything in. I'm just kind of thinking about it. Okay. All right, let's look at the last example here. So here it says sketch the graph of y equals x minus 2 to the fourth plus, or times, I'm sorry, x plus 3 to the third times x minus 1 by finding the intercepts and, by finding the intercepts and using the limits as x approaches positive infinity or negative infinity. Okay. So at this level, not an unreasonable request would be for you to tell me the x-intercepts just by doing the arithmetic in your head. What would the x-intercepts be for this function? Excellent. 2, -1, and +1. Nolan, how did you do that so quickly? You just took each factor and set it equal to 0. Everybody kind of remember that? Okay. What would the y-intercept be? Equally reasonable to ask that we do this in our head.
0.
Excellent. You're plugging 0 in for x. So -2 to the fourth is 16. 0 plus 1 is, and then to the third, still 1. And then 0 minus 1 is -1. Everybody's okay there? Okay. And I'm just going to call this thing f of x because I don't want to write it down. It's a lot of stuff to write down. Okay. To do this limit, I'm just going to kind of think about it the same way that we just did when I was deciding whether negative infinity or positive infinity. Okay? So imagine I'm picking a very negative value and plugging it in for x. A very negative number minus 2 is
Negative.
still negative, but we're putting it to the fourth power, so it's positive. Okay. I do a very negative number plus 1 is still negative, and then we raise it to the third power, still negative. And then a very negative number minus 1 is still negative. So I have positive, times negative, positive. And because this is just a gigantic number that I'm plugging in, I know we're going to infinities, right? Does everybody feel okay there? Let's do the same thing now if I'm plugging in a positive gigantic number.
Positive infinity for the first one.
Okay, so I have a positive for the first one,
Positive for the second one.
and
Positive. Positive infinity.
so it should be going to positive infinity. Okay. Now we did that quickly. Do we need to clarify that? Was that okay? I'm going to continue to keep asking and checking in. I don't want to feel like I'm going too fast or buzzing through stuff that we're not sure about. So there's -1, +1, and 2. And then let's see. I don't know. Let's just make that 0, 16 down there, or 0, -16 down there. So I'm starting from my end behavior on the left is going up to positive infinity. Now at +1, the exponent here is 1. So how should this pass through the intercept? Oh, I'm sorry, that's not, we're looking at this one. The exponent is 3. How should that pass through? Chanel?
I have actually a question.
Oh, okay.
So how come this end that you just this arrow you drew, how is it x approaches, is this x approaches negative infinity, f of x equal positive infinity? So wait, so how is it positive infinity?
It's pointing up.
So, because you're
The
going
y
to
is
left and then up.
the y is the limit, and the x is the x approaches.
It's the approaching, yeah.
Yep, that's okay. So back to my question. How is that graph, how's the line on the graph going to pass through that x-intercept
Goes down.
if the degree is 3?
Doesn't it go down?
It's going to go, well, it's going to pass through it for sure, but it's going to look like a bend. Remember, if that number of times that 0 is used is odd, you have that like the bend. Remember when we did solving polynomials generically in either pre-calc or algebra 2? The next one is positive 1. There the exponent is 1. That solution occurs 1 time, so just is going to pass straight through. And the other one is used 4 times, which means it's going to be a bounce, is what we called that. And because the end behavior, again, should be going to positive infinity, we know the arrow just points straight up. So there's my picture. Now, the bend, bounce, straight thing, I don't think that anybody would be caring too much about. I think what we would really need to see is those details. And if you hit those details, I don't think anybody's going to care about like how things are passing through. The tough one to get correct would have been the bounce, to think to just hit it and then come right back up instead of trying to pass through and create an extra intercept that you're not supposed to have. Right? Yes, Shizo. Bounce. Any evens or bounces, any degree greater, or any odds greater than 1 are bends, and exactly 1 is a straight. You're welcome.
So the stuff to the third power, that's a bend?
Yeah, so you see how it kind of like
it folds in?
Yeah, like
that. Okay.
yeah, where it changes from being like up here where we're like concave up here, like if you poured water, it's like catching it. And if this part is concave down, if you poured water on that, it would like run off.
Oh, okay, yeah. All right.
So it's like half a hill and half a cup.
Looks like a snake.
Yeah, sure. Looks like a snake. I think of cups and hills, but you know, like whatever works, right? We're just making analogies. Your analogy is just as good as mine is. Okay. Nolan, you said you had some homework question, right?
Yeah.
So let's transition here to some homework questions, and we can do a couple of those.
It might have been answered today, but I'm not sure.
That's okay. We can go and look at them still. Remind me the numbers here again, though.
29 and 31.
29. Okay. Okay. So if we look at this, this is a rational function, right? Oh, there's one other thing I want to circle back to, but we can hit it in a second. So I can, if this is a multiple choice question, I can just do this by degrees, right? What's the degree in the numerator?
Bigger than that.
Bigger than the denominator. So it's either going to be positive infinity or negative infinity, correct? Which one? Well, if this is a big positive, this is like a 3 pluser, that's a 1 pluser, and that's like a nothing, right? So down here, even if you do minus up 1 pluser, it's still going to be a positive number, right? Up here, this is like a 4 pluser minus like a 2 pluser plus a 1 pluser. Again, still should be positive.
Yeah, I plugged in big negatives for some reason.
Oh, sure. So it should be that, right?
Yeah.
Now let's see what we would do algebraically, right? Like if I actually had to show work. So I'm going to multiply the top and bottom of this by, should I do 1 over x cubed or 1 over x to the fourth? Cubed is correct. Because I don't want to zero the denominator out. So I would say that's sufficient work. Chanel?
So if the degree of the denominator is greater than the numerator, what would you do instead? I forgot.
It's 0.
0? Okay.
Nolan, does that feel okay?
Yeah.
Okay. Before we do 31, I forgot there was something else here that I wanted to talk about because I'd left you guys with a question here at the end of yesterday's lecture. I'm going to grab that and take it someplace where we have a little bit more space to think about that. Okay. I'm going to change this. This shouldn't have been x to the n. I don't know what I was thinking. I want it to be x to the x. All right. Ranking these by growth rate. Which one is the slowest? 2. Great. Why is that? Because it doesn't grow at all. It's just a flat horizontal line. The growth rate is ostensibly 0, right? Good. What should be next?
X equals x.
It's not x.
H of x.
It's what?
F of x equals h of x.
That's ln x is the last thing.
Oh.
And it's that one. The natural log is the next slowest growing one.
I thought it was h of x.
Oh, my apologies.
Yeah, so I just made up some variable. No, it's like x minus 1.
Okay. Should be the natural log. That's what that's supposed to be. What's next? Square root of x. Excellent. Then what?
Equals x.
X, yep. Okay, we gotta be careful now. We have 2 to the x to the x, and x factorial, right? 2 to the x is the next answer, because that's 2 multiplied by its 2 x times, right? Not x to the x. It's x factorial. So think about x factorial. That's x things multiplied together. X is the first one, and every other factor after that is going to be less than x, right? X minus 1, x minus 2, x minus 3. But x to the x is x times x times x times x times x times x. So each factor there, after the first one where they're tied, every factor after is bigger, right? So like x to the x is So like x is bigger, x is bigger, x is bigger, x is bigger, x is bigger everywhere, except for that very first multiplication, which is tied. So definitely x factorial is smaller than x to the x. Are we sure that x factorial is bigger than 2 to the x? Yeah, because 2 to the x would just be 2, 2, 2, 2, 2, 2. So the only spot it's bigger is right here. But everywhere else, it's either tied or smaller. So, yes. I'm assuming when x gets huge, infinitely big, definitely the factorial is bigger. Nolan.
Is this like going to be in the test, or is it just kind of...
So why are we talking about this? I'm talking about this to help use as a foundation to create some intuition to where you can look at a limit problem and not have to do something algebraic to it and just be able to come up with the answer. For example, I write this. We can do this in our head with no work at all if we understand how to use this idea up here. What's the fastest growing part of this limit that I've written? The e to the x part. So this is really the same thing as just 1 over e to the x. All the other stuff doesn't matter because e to the x is growing way faster than all the rest of it. So this is just 0. Because I have something 1 over something huge going to 0. Chanel?
I don't. So when you think, so like 1 over infinity is equal to 0?
Yeah.
Oh.
Right? Because if so 1/2 is 0.5, 1/3 is 0.3 repeating, 1/4 is 0.25. As that denominator gets bigger, the decimal expansion keeps getting closer and closer and closer to 0. Right? That's what we're saying. So again, the idea here is like, this is like, really I could lump, this is like any polynomial. Doesn't even matter the polynomial. This is any exponential, right? So like if I look at something with polynomials, exponentials, radicals, natural logs, all this stuff all crammed together and I'm doing the limit of it, I don't really care. I just want to, what's the fastest growing thing? Is it the numerator or denominator? That's all I really care about. I can only do this with limits at infinity, but this is helpful, right? To just be able to look at it in a multiple choice setting and go, oh, this just boils down to the fastest growing thing. Where's that at? Numerator, denominator equal on both. Then I'm just going to use the same rules that I did for a rational function. Fastest growing thing on top, plus or minus infinity. You have to think about which one it's going to be. Equal, leading coefficient over leading coefficient. Bigger on the bottom, goes to 0. That's all I care about. Chanel.
So how come it goes down to like, what's the fastest growing thing?
X to the x.
No. How come like, if you know like the fastest growing thing, you can automatically help you find the limit? Is it because like, it's like over y and stuff? Like,
Yeah. So like if you think about, if I graph like y equals x, right? If I graph e to the x, looks like that. Comparatively, when you get way out here at positive infinity, this is doing nothing. This is exploding, getting bigger so much faster that like x doesn't matter. It might as well just be holding still because that's how little it's changing when the x is getting really, really big.
Okay.
When we're really far out here. So just the fastest growing thing is really all that matters.
Okay.
Does that Make sense?
Yes.
Okay.
So fastest growing thing will like reach the limit first, right?
It just turns into like that's all that matters.
Yeah.
And when we get out there, the other stuff might as well not be changing in comparison.
Yeah.
That's the idea. That like the other stuff is still growing, but comparatively, it might as well just be holding still. It might as well just be a constant. Because the difference in the rate at which they're changing is so massive as to not matter. Okay. I'm glad I remembered to come back and do that. I think that's a really useful like piece of intuition to have, right? That it just comes down to like what's getting bigger faster. Nolan, you said also what 131 you said?
31, yeah. I think it's probably also better.
Yes, I think so too, but that's okay. It's that one. So again, you should hopefully look at this and be able to tell either positive infinity or negative infinity, right? Let's, let's see. Right, I'd start by factoring off an x to the fourth. And then if I do x plus 1. Okay. If I look at this limit, that's going to positive infinity. If I look at this one, it's going to negative infinity. If I multiply a giant positive number and a giant negative number, I get a giant negative number.
That would be enough for the if it was an FRQ, right?
Yeah, in fact, you wouldn't even have to include this part. You should not, in fact.
And multiple choice, do that in your head.
Could just do it in your head if you wanted to. Yes. Katie. Yeah, for sure. And this is not simple, though. This is like, it looks simple when you look at it, but it's not. I mean, this is like, it took 4 sections to build up. And like, to actually do this algebraically, I had to factor. I had to use a limit law. I had to use the, like limits at infinity. I had to use like 3 separate kind of tools together to answer that. I mean, in the end, yes, it should feel simple, but like it's not from the AP standpoint. Like I had to use 3 tools to do that. 2 of them being like something you would not have seen until this course. Like factoring, obviously. That's not trivial. But. Chanel.
Can you do number 14, please?
14. Mm-hmm. Okay. So it says evaluate the limit and justify each step by indicating the appropriate properties of limits. I would say that you do not, I wouldn't need you to do that. The indicate, I would just say like show your work enough that you're using your limit properties.
Oh, like not say number.
Yeah, I don't need you to say whatever. That's stupid. Like it's trying to, I understand what the question is asking you to do that. It's trying to get you to go back and like, what can I do with this? Why can I do that?
Okay.
Right? To just do one property at a time, but I don't need you to like quote the numbers.
Okay.
Because that's just like, too much flipping. Back and, like hunting for what is this one called? What is this one called? What is this one called?
Number 27.
Yeah. So I would start by doing this. Why do I need the radical over it?
So you can multiply them.
So I can multiply it inside the radical, yes. And then here I'm going to use my continuous function that allows me to push the limit inside the radical. I think that was also a limit law.
Yeah.
And then I can distribute my limit to each one of these.
Okay.
And then I can pull off the constants. So I'm going to do both of those things kind of all at the same time. And I didn't write my radical long enough. Yeah. Oops, I forgot to put the over x squared in there. Now remember, got to hang on to those limits until they actually go away, right?
So I think you're gonna go like mark this down if we
If you just dropped your limit, like after that first step, and you didn't even continue to follow it, writing it through, I don't think anything afterward would warrant any points. I think you would get nothing on a free response graded question if you went at this step. If you lost your limit and then lost it all the way through, I don't think you'd get any points for that. Even if if everything else, if the limits were there, would have been the right thing to do, I don't think you would get anything for it.
So what is zero? Is zero like anything 1 over x? Like 1 over x squared, 1 over x cubed? Like
1 over x to the n goes to 0 at either positive or negative infinity.
okay.
Yes.
Couldn't that basically be anything over x to the n? Because you end up just taking it like in front with something zero anyway. Like 2 over x to the third x cubed is still a 0.
Right. But it said to use the limit law, so I'm trying to
Okay. So
not, because the theorem doesn't say a over x to the r is equal to 0. It says 1,
is there a reason it doesn't say it?
because you already have the coefficient property before to just,
So once it's
so it doesn't, you don't need it,
okay.
I guess. I'm just following directions, you know what I mean? But yes, you're absolutely right. It does not matter whether you pull that out or not. I'm just trying to follow the directions on the problem.
We would get less points if you didn't do that in AP.
I don't think it would matter, to be honest with you.
Okay.
I don't think that would matter unless it was like, show that this is equal to this, but I don't think they would ask you to do that. Chanel, are you happy with?
Yeah, that makes sense. Thank
Okay,
you.
certainly. Anybody else? Katie? Sure. Oh, you concerned about the square root?
A little bit.
Well, what's the degree on a square root?
1 over
1/2, right? That's all I'm doing with it. So I'm still going to do just this.
Did you rewrite the root t as like t to the 1 over 2?
So this would be then t to the 1 over 3/2. And if I do my limit laws, then
I did that. I don't know why I didn't first.
awesome! That's exciting. Yeah, 100% that's what you should have done. Again, if we think about this from like what's growing fastest, the t squareds are growing fastest. Nothing else matters. So it's really just t squared over negative t squared. -1. Done. Yes, Chanel.
So for like when you're evaluating if it's 0 or not, it could be like any number over t, like as long as it's like a rational, that's an irrational.
If it's a constant over any power of t,
Okay.
I should say any rational number power of t.
Okay.
If it was t to the pi, can't say that's 0 even though it's 0.
Okay. And then you can do this like this kind of method where you multiply like the 1 over t squared, the root 1 over x, that kind of thing, or if it's only going to infinity.
It is most appropriate when we're doing infinities, but when we multiply by conjugate, this is still the same thing that we're doing, right? Because that's really just 1 is all I'm doing. So it's the same idea as when I multiply with the conjugate.
Oh, okay.
It's still kind of the same thing.
Okay.
But yeah, this is when we do like 1 over some power of a variable to some power. Almost always it's going to be for an infinite or limit at infinity.
Okay, so if t is like approaching a number though, would it be like you'd have to use like a graph or like a table like we did earlier?
Or you can probably just do direct substitution.
Oh.
Or you might be able to factor and reduce. Or you might be able to, like do one of those sorts of things.
Okay. All
Right?
Thank you.
Uh-huh. Okay. Look at this. Okay, so that's nothing. Let me go grab that. Copy. Content library. Delete this one. And put this one in. Okay. What's up?
It's raining outside.
Oh.
And I parked super far.
Oh, no. All right. Let's talk a little bit about the test. I know that this is still, like we have Monday still in the test scheduled for Wednesday. I assume some of us are going to want to start looking over things during the weekend, possibly. So I want to make sure I have a chance to talk about this before then.
Sorry, did you say that this was Wednesday?
Mm-hmm. That's my plan. So your test is going to be broken into 2 parts. The first part is no calculator. It's going to consist of 10 multiple choice questions and then 1 free response question. By free response, I mean like a normal written question, but it might have multiple parts. Okay. Part 2 is going to be calculator option. You can use it if you'd like. You're going to have 7 limit problems and then 1 free response question. So the skills that you should be able to demonstrate are using a graph to determine a limit. That includes the limit of composite functions, like when we did in the 2.5 bonus stuff, where I gave you like the 2 graphs and looked at like the limit is, blah, 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 for like h of g of x or something. You should be able to use a table to determine a limit. You should be able to use algebra to determine a limit, particularly in those indeterminate cases. So remember our methods, algebraic methods to evaluate a limit were direct substitution, FOIL and simplify, factor and reduce, multiply by conjugate, make a common denominator, absolute value functions. What do we have to do with that?
You split 1 into positive and 1.
Right, you look at the left-hand limit and the right-hand limit, and then look at, using splitting either like positive version of it or negative version of the absolute value. Mm-hmm. And then our limit at infinity techniques that we've talked about in 2.6, so like multiplying by 1 over x to the n, or, like using that, limit as x approaches negative infinity, e to the x is 0, that kind of stuff. Should be able to apply the squeeze theorem to determine a limit, apply the intermediate value theorem to show a function takes a specific value, use a limit to show a function has a horizontal or vertical asymptote, know the 3 different types of discontinuity and be able to identify them from a graph or a table or a limit. So the 3 different types are infinite, like a vertical asymptote, jump, where the 2 ends don't match up, and then removable, where the 2 ends meet, but it's open, whether there's a point there or not. Chanel.
What does it mean that identify them from like a limit?
Like if I gave you, if I said like the limit as x approaches 2 from the left of f of x is 6, and the limit as x approaches 2 from the right of f of x is 3, you know that's a jump.
Jump discontinuity. Okay.
Because the left-hand limit and the right-hand limit aren't equal.
Oh, okay, got it.
You know, like that's what I mean. So if I just give you that and I don't give you any way to like generate a picture from f of x or generate a table from f of x, I just give you information about the limits.
Okay.
You should be able to do that still. You should be able to demonstrate whether a function is continuous or discontinuous at a specific x. And then know the types of functions that are continuous over their domains, so that you can use that information to do the intermediate value theorem or justify whether I can push a limit inside of a function or things like that.
Do you think we will get any functions that aren't continuous over their domains?
I mean, you saw the list.
Is there even any functions that we've learned about?
Well, I mean, like, if you think about a piecewise function, technically that's not continuous over its domain because the pieces don't necessarily have to hook together.
Yeah.
But each piece has been continuous over its domain.
Okay.
So, like, take with that what you want.
Okay.
Okay, Katie.
Do you have to write that whole since f whatever is less than 0, which is less than whatever, for the whole statement for the intermediate values there?
If it were a free response question and you needed to use the intermediate value theorem, yes, you'd have to like justify that, like explain how you met the hypothesis for the intermediate value theorem, and then because of that, you can state the conclusion from the intermediate value theorem. Yes, you should be able to use that kind of notation. If it's a multiple choice question, no. So in addition to reviewing the skills above, I put some questions on my AP that would be worth looking over. So I have the Unit 1 progress check, which are multiple choice questions. I ask you to skip 2 through 4 because they involve a topic we haven't talked about yet. And then for the free response practice, I asked you to look at Unit 1 practice level 1, 2, and 3. Level 1, you can skip part A, and level 3, you can skip part A because, again, they're referencing something we haven't talked about yet. And then I'd recommend, again, looking over these homework problems that I've listed here, as I think these ones are quite similar or fall in neatly to these, particularly to these skills that I've listed. I think the way that they're asking the question, like, hits at the concept I'm looking for is like appropriate practice for the kind of limits that you'll be asked to do. So this is going to be your study guide for this one. Now, in the future, will all your study guides look like this? No, they don't necessarily have to. They could be better, right? They could be more specific. This chapter, this material we've done so far, is very conceptual, right? There's not a lot of, the problems that we've done aren't tremendously complicated in that they require a lot of writing or a lot of work to get to your answer. But you really have to understand the concept, right? They're very conceptual. You have to think about, like, okay, what does that mean I have to do? You probably spend more time thinking about what do I have to do than actually doing it, right? As a result, it's very hard to write a different version of the question that's not just like the same question. And this that we're doing now is like the underpinning of everything else that we're going to do. So the three main topics in your first year calculus course is the limit, the derivative, and the integral. The derivative is defined as a limit of something, and the integral is defined as a limit of something else. So like the limit is here kind of like the engine, the underpinning of all the stuff we're going to do. So this conceptual understanding that we're trying to build right now is going to be really important going forward. So I want you to study these things in a way that, like, you don't learn them for today or for the test day or for the week, that, like, you know them in your bones so well that, like, your children will know this, right? Because it will pay dividends as we move on. Some of you are like, I'm not having kids. That's fine. I'm being facetious, but that's part of the reason why I'm giving you like something that's kind of vague as a study guide. It will not always be this vague. As we move forward, things become more symbol pushy, which means I can be a little bit more specific in the work that I give you for a study guide, because it's mostly about like pushing the symbols around and doing some algebra. Here, there's much less symbol pushing. It's very much more conceptual. Do you understand, like, what do these things mean? Like, how do I show mathematically that this thing is doing this or not doing this? So that I want you to really kind of like think about. And the other piece is, probably most of us in this room will be taking some advanced college math classes. And I've had math classes where you don't even get this. You get like, okay, the test is on chapters 1 and 2. Good luck, we'll see you next class. You know, where it's like, okay, so what do? You start by making a list of the major concepts that you talked about in class. You go through your homework and try to figure out like what problems fall into what concept category. You go look at like, okay, what did we spend the most time doing? Make sure you really know that stuff. If you have time, you can worry about the minor stuff. But this is exactly what you'd want to do if you're not given anything, right? Is to go through and look at what are the major ideas, go through the homework and see which problems fall into which kind of ideas, figure out kind of like how much, like which of these ideas is the really important stuff that I have to know, which of the other stuff is like, I remember he got real excited when somebody asked a question about this one. I better make sure I know how to do that kind of situation or deal with that. But this is what you'd want to do. So in a way, I also want to like take this as an opportunity to model this as well for you. Again, I'm not trying to make this harder than it needs to be, but for a conceptual set of topics, if I give you something super specific, you're going to just study the super specific thing and kind of miss the general conceptualness of what's going on, right? Like you'll think about, okay, just to do this problem, I use this trick rather than like anytime kind of something looks like this, I can do this trick, which is where we want to be getting to. So I just wanted to like talk about like my rationale for giving you something that looks kind of general or more general than you maybe were expecting. The AP stuff, keep in mind when you do it, you're going to get instantaneous feedback. Like as soon as you submit, it'll score it for you and display what you did. I think you can see all that right away. And the homeworks are all things that we've done and probably talked about most of these questions as they were, I think, important ones. Or were ones that were like, there's an odd answer and maybe nobody asked about it because it was odd and they checked it. It's like, okay, that's what I got. Good. Yay, moving on. Next class, the plan would be to let you bombard me with questions. We still have to do the 2-6 homework quiz, but like that's 10 minutes. But the rest of the class I would leave open for you to bombard me with questions, whether they're from the MyAP or their homework or conceptual or whatever. My favorite color maybe? I don't know. But that's all fair game for you guys. Wednesday is our tentative test date. If come Monday that becomes a really unrealistic day because like, oh my God, there's like 4 other things going on that day, we can talk about it then, and if we need to move it, we can move it. We'll just start the next set of contents on Wednesday, which is not what I'd love to do. I think there's no reason to push, but if it's, like a mental health push that we need to do because like, oh my God, like 2/3 of us have this thing and it's all due and it's like, I'm going to go grab it. We can handle it. But that's the plan. Is everybody okay? So the problem set for this weekend is 2-6, right? Is there anything you need to do for the review? This review is just for you. The questions on the MyAP you can do or not. If you want to sit down and do them with your friend and just submit one thing, like it doesn't matter. You don't have to do them. I would recommend that you do them. I think they're excellent practice. That's why I've chosen them, but you don't have to. There's no grade attached to them. Brooke.
So 2.4 isn't going to be on the test.
Correct. Nothing from 2.4. Yeah, absolutely. Yes. I just wanted to talk about it for a minute because if you're a future engineer, it's something that you would do in your Calc 3 course, but that's all kind of a long ways away, and it's not an AP topic. So I'm just wanted to kind of like talk about the idea and spend 20 minutes or something, and then go.
It's okay. I'm not going to engineering.
That's
so
okay. It's okay. It's okay. All right, everybody good? Feel okay about like what's going on and what to do and what to expect when you're expecting a calc test?